All right. Thank you all for coming. I think this is the seventh, eighth seminar we've had. And today we are fortunate enough to have Ruben Arts with us. I believe he met our own Julia Marcel back earlier this year, back in FOSDEM. And he was kind enough to sign up to tell us a little bit about Pixi, which I'm pretty sure a lot of you already if not familiar, at least acquainted with. But before I pass on the token to him, I want to give you a sense of who Ruben is. Ruben is a software engineer from the Netherlands who originally worked on and studied robotics, and I guess to surprise of no one, he found that developer experience in the ecosystem was somewhat lacking. So he joined Prefix.dev to try and change that by building on top of the conda ecosystem and environment into something that's fun and exciting and useful. So there we go. So with a focus on outreach and community, this is our chance to meet with him, to get to learn a little bit more about package management, and hopefully get all our doubts and questions addressed. So without much further ado, Ruben, the floor is yours.
Thank you, Miguel, and I hope everyone can hear me well and see the screen well, so I can present you Pixi for robotics. First off, thanks to you guys for coming to let me share our work. We're very proud of what we've built so far. We've been working on it a few years now, and I hope I can not just tell you how it works, but also slightly convince you that this way of working is going to be an improvement in the future of robotics. And I hope you, if you're not using it already, will give it a try later and let us know how it works. If you've already tried it and there's issues, then also let us know. And if you've already tried it and you really like it, then please let me know as well, because that really motivates, and I love to hear from you guys how you're using it. We'll talk about Pixi today in the most bare bones form that it is, and especially in the robotics ecosystem. So what does it mean to go beyond Ubuntu and the ROS distro using Pixi? I will continue my own introduction that Miguel just gave with a little bit more information. So as said, I'm Ruben Arts. I'm currently a developer at Prefix.dev. I studied robotics and I joined RoboCup. Maybe some of you have heard of that. This was my baby for a few years, just developing on a AGV with a robotics arm. This really got me started and really excited about ROS and robotics in general. That made me start my internship and afterwards my first job at Smart Robotics. I've worked there as a core developer, meaning that I wasn't so solely focused on the application itself that we deliver to customers, but mostly on how do we do motion planning and how do we do the basics of the robotics side. And that eventually led to developing a developer workflow for our internal developers. So I was mostly focused on how do we install environments, how do we deploy to customers, how do we make sure that our CI is efficient and stuff like that. And that kind of set the stage for me joining Prefix. So Prefix.dev is a company that focuses on package management, and I joined there to solve my own problems with a team that's also basically built up of robotics engineers that figured this is one of the biggest problems and we have a way to solve that. My CEO, Wolf Fulprecht, was also a robotics developer, started building ROS packages into the conda ecosystem, and that kicked off the whole ability to use the conda ecosystem for ROS. And this is what I will tell you more about today. Why am I the one that's telling you this? It's because I really like to do these kind of workshops and outreach and demos. I've presented at ROSCon and many other conferences over the last years, sharing the word of Pixi, basically being a saint at this point on how to use Pixi. And yeah, hope you like it, and reach out if you want to know more. So let's first talk about what is the problem that we're trying to solve. Within the robotics ecosystem, there is a big lock-in on the Ubuntu ecosystem, and that mainly means you have an LTS version of Ubuntu and a ROS distro built on top of that, and next to that you just need to scramble your tools together to get it working. Most often you will have Ubuntu with a ROS distro and then pip, which is all globally installed, and that is constantly breaking. There's a lot of different ways to avoid this problem in the current state, but I think for most cases in universities and everyone, they're just saying install an Ubuntu version and then continue from there. That's something that I really want to get rid of, and I will present to you today. Then if you have that set up, there's no log file. So it's basically in your shell history what you actually did, how you got it installed. It's based on some readmes that people provided you, and you're basically reliant on the open source maintainers of these tools to not break that setup, because if you later install something on a different machine, you might get totally different versions, especially with the pip part that moves a lot faster than the apt ecosystem. And you can suddenly not recreate the exact same application that you were doing, making it really hard to do demos, making it really hard to deploy. And this is obviously very hard if you want to do cross-dev and robotics development. So you're probably not going to run the code on a developer machine. You're going to run it on a separate computer that's linked to the robot. Maybe it's not even the same type of OS. So maybe you're running it on a Jetson or on a Raspberry Pi or something completely different. And that's a problem that's hard to solve if you're locked into this one distribution. And then everyone these days reaches out to Docker to be like, okay, but if I build it into an image, I can then ship that image. Basically, the joke that you're shipping a whole computer to get your thing reproducible. And while I think this is a really great way of getting this stuff done these days, it's not a full solution, because within these Docker images, you still need to be able to install the packages, and if you want to recreate the same image, you're still depending on the maintainers, and you're still going to get incompatibilities between these setups. So without any form of log file, these Docker images are also not reproducible. This is all something that we with Pixi want to try and solve, and especially in the robotics ecosystem, this is very interesting. So what is Pixi? Pixi is an open source project, and you can all access it through this link. It's freely open source, so you can also build on top of it if you want to. Please fork it to keep it online forever, because that's why my goal and our company's goal, obviously. And then what is it? It's a cross-platform, cross-language package manager with a built-in build system. So if you think about what does that mean, it's like apt and pip in one tool, and that's on all platforms. So what you do with apt, you can install Python, you can install CMake, you can install all these crazy low-level packages, and then often you will divert back to pip to install your libraries for your own application. So for instance, PyTorch or some other tooling that you need. And these are two different ecosystems, and you're obviously mixing them together. Pixi can do that for you. So Pixi can install both PyPI packages and basically the packages that you would normally install with apt, like Python, like CMake, and that's cross-platform. So this tool can be used on Windows, Mac, Linux, and I will repeat that very often. I've been told that I repeat it too often, so be prepared, because I just can't stop with that. Then it's built on top of Conda and Conda Forge. I will tell you more about it later, but this is the basis that we're basically not reinventing the wheel. We're just improving the tools around an ecosystem that was built already, like I think around 15 years now. So we're not reinventing the whole idea of a package manager or the idea of a package. We're just improving the tooling on top of that, making it faster. We built everything in Rust, and that's not per se making it faster, but it allows us to use an incredible set of libraries to just improve this ecosystem as a whole, and we've been doing that for the last few years. Then Pixi itself, where normal package managers like apt and pip, they will do something on your machine in some directories on your machine. Where Pixi, we didn't like that. We wanted it to be declarative, meaning there is a file that tells you what you have done and then allows you to recreate the exact same thing from that file. And that is the Pixi toml, that is the main manifest, and it will list all your dependencies, and it will list a lot more. I will come back to that. But then after you have set that up through the CLI or just manually editing it, you can create a log file next to that. Pixi will always give you that for free because it's part of the it's an artifact of what Pixi does when it runs. But you can commit that to Git, and then you can later create the exact same environment again, not just on I depend on Python and I depend on PyTorch. No, much more low level. I depend on Python, meaning I depend on this bzip2 package that is needed in the Python executable. It goes down completely back to the glibc version, and that means that it can run on any Unix distribution and even on Linux. And even on Windows. So it supports the binary distribution of these conda packages, but it actually also has something cool that it can do source building on top of that. So similarly to pip, where you can just build pip packages, with Pixi you can build conda packages, and I will show you a little bit of an example later. And then this is not for everyone, but it's perfectly suited for people that do multi-language projects. And this comes back to being very good case for robotics. You often mix Python and C++. These days, Rust is coming in. You often have a UI built in some kind of JavaScript setup. You might have some really data science heavy projects that use some Fortran or R, and that's all manageable through this one package manager. And then this is already being used a lot by the data science and AI and ML ecosystems. This is actually currently our biggest user base because the conda ecosystem has roots in that ecosystem. And with Prefix, we're really trying to also move that into robotics because we think it's so well suited for that. And it will work on our machine, just so you know. So should you really care about this? Is it just another project? No, it's just not any other project anymore. We've been growing it over the years, and it's already surpassing some of the bigger ROS projects that you might know of. This is not an exact measurement, and of course we're living in different ecosystems, but I just want to make sure that you understand we've been building a project that's actually being loved and used by multiple people. The ROS2 main repo already has a Pixi toml inside where you can use it to do some source building. Yeah, that's the source building. Then the RAI Institute, the Robotics and AI Institute, is also using Pixi across their stack to quickly install some of their examples. We've had a lot of fun working together with them, and they're also helping us grow the ecosystem within Pixi and RoboStack. And then, of course, your favorite, Davide Faconti, the builder of Plug Juggler, mentioned that he is promoting to install it with Snap. And then Open Robotics reacted to that, and he is already like, okay, but just wait, soon that will be Pixi. People are catching on, and at the ROSCon, we got a lot of love. I'm currently working together with the Isaac team to also make the documentation and tutorials for their ROS integration, all based on Pixi. So it's just an easy single command to also get the Isaac sim started together with a ROS environment. And as we're going, a lot of small projects are adopting it. So if you're interested and if you want to join in, join our Discord so we can talk about it. And it's not just me helping you out. There's a lot more people that currently can help you out with how to install your ROS packages with Pixi. So to go a little bit deeper on what the grounds are that Pixi is built on top of, the conda ecosystem is not just a package manager, it's a full ecosystem. It has build tools, it has install tools, it has hosting services, and that's not just by our company or the original makers of the conda tool, which is Anaconda, but there's much more vendors available already. The conda ecosystem is built so that you can compile any type of language into a conda package. So you will see a lot of C, C++, Rust, and Fortran, because those are basically the basis of what the Python ecosystem was doing years back when they started conda, because the conda ecosystem was built for NumPy and Numba, which are the initial creators of the conda ecosystem were also the builders of NumPy and Numba. So that's why it relates so much to the Python ecosystem. But that doesn't mean it's a Python package manager, which everyone always thinks, and that's a name that I want to get rid of. If you build a package with the conda ecosystem, you will upload it to a channel. And this is just a different name that every ecosystem has a different name for. The Python ecosystem uses indexes. So PyPI is a Python package index. The Ubuntu ecosystem uses repositories and distributions. So everyone has a different name of it. Just know if we talk about channels in the Pixi setup, we talk about a hosted set of binary packages that have some metadata next to it so that Pixi and other installers know how to install these things. So just know that because it will come back. And then if you build a conda package, you will use a recipe. And for instance, it's like a package XML, which defines the dependencies, and then a CMake list that defines how to build it. And it often just contains, it's just a YAML file that says, I'm this package, here's my source, these are my dependencies, and this is the script to build it. Also, recipes will come back later, so that's why I'm mentioning it. It's not as scary as it sounds. It's actually pretty easy, and we might have some fun with it later. So then what is CondaForge? All these names will maybe startle you in the beginning, but if you're getting used to it, it's not that complex. The CondaForge is a open source, community-managed distribution of conda packages. Currently, it has over 30,000 packages, and that includes Python, that includes CMake, that includes all the compilers, that includes some CLI tools like the GitHub tool and Git itself, for instance, and yeah, you name it, and it's often already on CondaForge. And if it's not on CondaForge, you can easily add it through these feedstocks. It's community maintained, meaning there's currently over 7,000 maintainers that all maintain different packages in the ecosystem. And often a package is maintained by multiple people to make sure that we're not breaking anyone's setup when we start making changes to these packages. It's curated, so every recipe that has to go in first goes through a review process, meaning that we don't just allow anyone to publish anything to this ecosystem. So if you do an installation with Pixi and you're grabbing it from CondaForge, it is assumed to at least have had a few eyes on the package before it was merged in, so that you don't start pulling some random things in, which happened a lot in the PyPI ecosystem, where people slightly changed the name and suddenly got a package they were not expecting to grab. And this then allows us to go to the next part, which is RoboStack. So I will quickly summarize. The Conda ecosystem has the Conda installation tool, and Pixi is another installation tool on top of that. Then we have CondaForge, which is a repository of packages that is community maintained and has over 30,000 packages to get you most of the packages that you need. And then next to that, you can have custom channels. And one of these custom channels is RoboStack. When RoboStack was started, it was trying to upload ROS packages to CondaForge, but quickly noticed that there's over 3,000 different packages. Moving that into that ecosystem that works with a repository per package is going to give us 3,000 repositories of packages that we have to maintain. And when it started, it was just a few people that wanted to get ROS on this Conda ecosystem. So they decided to make it built on top of CondaForge. So using the Conda packages from CondaForge, such as Python and the compilers, but automatically generating the recipes and building the recipes in some CI setups to go from the ROS index to a channel that the Conda installers can use. And out of that came the RoboStack channels. So you have a channel per distro, so Humble, Jazzy, Noetic, etc. They're decoupled from any Ubuntu distribution because it can use Python and compilers from CondaForge. You can install it basically anywhere you can install CondaForge as well, thus allowing you to install Humble and Jazzy and Noetic on a Mac or on a Windows machine or on any version of Linux. Basically completely getting rid of the lock-in that we're currently experiencing. And then this is all automated through some tooling in the RoboStack distros. So if there's an update, we can call a rebuild, and we can rebuild the whole distribution based on the new updates. This is currently also what's going on for the rolling releases, so that we can get ready for the lyrical distribution that's very close by. So back to Pixi, because this was a little bit of a background of the tools that we're going to use in Pixi. Pixi starts out with a Pixi toml, and I will quickly show you, just so you have a feeling for what a Pixi toml looks like. If you call Pixi init through CLI, and you give it, for instance, the RoboStack, Humble, and CondaForge channels, it will create you a simple file that just has the bare minimum, basically saying, okay, I use these channels, and I use the platform in general, it's only the platform that you're on right now. If you have multiple platforms, you can just add these to the list. And adding a platform means my project is going to support this. So every time I add a dependency, I also want you to make sure that that dependency is available for these platforms and lock that down in your log file. Then we can add a dependency through Pixi add. This is similar to pip install or apt install. It will add that then to your Pixi toml as well to get that declarativeness that we talked about. It will automatically also pin the package. You can configure how you want this pinning to behave, but in general, it will do normal semver pinning, meaning if I have a 0 as my major version, all the minor versions are locked in. So if I do a resolve or an update, it will stay within the bounds that I expect my code to still behave properly, meaning the major version or the development version. Then Pixi also has the ability to run tasks. So in the simplest case, a task is just the alias for a longer command. And in this case, I added the command sim, which has a ROS to run command in there. And it will run in its own shell. So Pixi ships its own shell that these commands will be running. So if you use, for instance, a $sign for a variable, that is cross-platform. So you can use that on Windows, on Mac, on Linux. And then when we run that command, so we do Pixi run that task sim, you will just run this ROS run in that environment that will be created. Pixi run will always make sure that the environment that it runs in is up to date. So if you've changed these dependencies and you didn't run Pixi install on it, it will make sure that it is installed correctly before you start running, so that you will never have a Pixi run of something that you thought was already set up correctly, and then testing the wrong thing that you were not expecting. It will always make sure that your environment is set up as you defined it in your Pixi tool. So that is a very manual way to set up a workspace. And this is fine if you just have a few packages that you want to get started with or creating some demos. But probably you already have a ROS workspace and you want to get started today. So what you can do is install Pixi ROS. It's a small extension for Pixi that you can use to move your current robotics ROS workspace into a Pixi toml. You will just run Pixi in it, Pixi ROS in it, maybe define the distro or the platform, otherwise it will ask you for it. And then it will result in a Pixi toml that contains the right channel, that it contains the right dependencies mapped from those package XMLs into the Pixi toml. And it will also add some tasks that will help you out, like the build command and the test command. It uses colcon under the, or not under the hood, it will use that colcon to do that, but basically replacing ROS step for you. This is the simplest way to get started. It will also list if it can't find packages that are not yet built for our ecosystem. It has a README with that can help you out how to add these packages to our ecosystem, and together we can make this a better experience for everyone in the long run. But you might need more power than this. You might want to actually also move away from colcon. You just want one ecosystem that manages all of your dependencies and source building and everything else. So this is also something that you can do with Pixi. Pixi, due to the use of CondaForge, can use all the compilers on all the platforms. So C++, but also CUDA if you're interested in the AI workflows that these days are much more important. Pixi can build from source when needed, either through using these recipes that I mentioned before, or to use specialized backends. And these backends that we have created so far are specialized per ecosystem. So for instance, we have a backend specifically built for ROS, which can do amend packages. And we have also a backend that's specifically built for Python or Rust or CMake, so that you can basically build any type of package into a conda package through Pixi without really needing to know which type of commands you need to run, how to set up these recipes yourself. And this is a similar workflow to how Python uses build backends like setup tools or Maturin to build different ecosystems into a Python package. I hope you can all see this graph well. I wanted to quickly visualize how that works. So for instance, the Pixi build ROS build backend reads a package XML, uses some CMake and pip to create a conda package, and then that conda package will be installed into your workspace. And this goes for every type of ecosystem that we support. And then the resulting Pixi workspace, you don't really you don't really even feel that it's built by Pixi. It's just a binary installation of your project, and you can use it as if it was built by someone else. This makes it very flexible if you want to do cross-compilation, cross-platform compilation, or if you just want to develop on your projects without building it into a channel before you want to test it out. So what does that look like? Here I have a setup of a ROS workspace that you might see very often. So what you add is this Pixi toml. There you define these dependencies that we just talked about. You can have some custom ROS packages in there. They often all have a package XML and some Python or CMake list complementary files, maybe just messages. What you can also do is not having ROS package and just using a PyProject.toml directly without a package XML that can define everything, because we can go outside of the ROS ecosystem. Like Colcon, you always need the package XML, but with us, with Pixi, you can build any type of package into a conda package. So I should have opened it up before. Yeah, what this looks like when you start adding it to your Pixi toml is you just define the path to the package XML. And as of today, this is in a preview state because we're just heavily developing more and more features around this. But just now you can try it out today already and move your development process to it. We're just adding more features, and maybe we'll change some definitions in the Pixi toml. But again, Pixi itself is a binary that you can install versioned. So if you want to keep this version working forever, you can just use this Pixi version, and then it will keep working. For ROS packages, you can say, okay, I want to specifically use this package XML. Then you don't have to do anything else. But if you want to do another package management format, for instance, the Python one for the segmentation package, you need to add the Pixi toml or a PyProject toml in there, and then you can just give the directory in the package XML, in the Pixi toml, and Pixi will look for that Pixi manifest and install it based on how you defined that manifest. Then if you have that build set up, you can actually publish your code very easily to a channel. So you just log in to whatever hosting service you use. Obviously, I'm going to present the one that we provide, the Prefix.dev hosting service. And after your login, you can immediately start publishing your packages to your channel. And then your teammates setup, or you can actually prepare it for him, can add your channel and immediately start downloading the packages from there, adding that one package that you just built immediately. And this allows you to really simplify the workflow of moving from development packages into something that an integrator is going to test or is going to be moved to a customer, because there's no more source building needed afterwards. Everyone's going to be testing the same things. The build machines can be in CI, and then your local machine can be just the bare minimum that you need to run your application. The quick building is not a problem anymore, and there's no more build issues at the test setup. This also allows you to really lock in what you're testing, so you don't have to be afraid, oh, I'm using a different CMake or I'm using a different compiler. This will all be solved by just having your binaries pushed somewhere and pulled again when you need them. And of course, you can test it out today on Prefix.dev. We have a free trial to get started, and if you want to use more, then contact us or go through the website to get started. You can go a little bit further. You can actually auto build from CI. So if you do updates or tags, you can quickly spin up the build or the publish of your packages. And you can also actually sign your packages off so that you can really trust what you're building and then also downloading on your machine. If you want to ship to a robot that has no internet access, you can actually use Pixi Pack. It's another extension, and it allows you to completely pack up an environment that you have and then ship it through a USB stick or something else, because you just get an environmental tar file out of that, and that ships everything that you need. You can then just call Pixi unpack. It will install that directly, and it will give you an activation script. And after running that activation script, your whole ROS setup is done. There's only one file that you have to move over, so this makes the process very simple. This is often used for people that don't have any other understanding of how installation stuff works, and you can just tell them, use this tarball, unpack it with this one command, and then you're good to go. You can start working on your robot setup. And because of the isolated environments that Pixi creates, you can do multiple of these on the same machine. So what we've often see is that testers will get these tarballs, and they will just install them next to each other. And then for every single project, they will just put it up, activate it, run the tests in that file, and then they can just throw it away and start with the other project. Because Pixi isolates everything, you don't have to worry about these two different environments colliding and breaking each other's setup, making it much more easy to collaborate on one single robot setup, which was a huge issue for us when we worked on it. And yeah, again, there's no internet access needed. You can just ship these with a USB stick. You can also prepare them for an architecture that you're not working on right now. So if you want to ship it to, let's say, a Jetson, you can already tell PixiPack to build a archive for a Jetson. And then one cool feature that is often overlooked, Pixi can actually do global installations of tools. It's similar to how you currently use apt or maybe pipx, where you just install tools into their own virtual environment. I use this often for the GitHub tool, the Git itself. Maybe if you want to do only Python stuff and you don't care about Pixi, you can do UV, but also Nvim is on there, so you can go crazy. It will install everything into the bin folder, which is added to the path, and you will actually also have a shareable manifest that looks something like this. So if you keep your dot files in the GitHub repository, if you add this Pixi global TOML to your dot files, you can easily recreate your same setup everywhere using this installation tool. So I hope that was already interesting for you. I will start now to show a little bit of a live demo, but maybe there's already some questions that some people have. Then I'm already open to answer them before I switch the screens.
We can go whichever way you prefer. We usually do questions at the end, but there are already 3 questions ready. So what do you prefer? Demo and questions, or questions and demo, or both?
Let's do some questions first, and then maybe I can show it directly in the live demo.
Okay, that sounds great. So we have 3 questions. The first question is, and for those that don't know how or where to ask the questions, if you go bottom right 9 dots, look for Q&A, and you're going to find the list of questions over there. That's it. The first question is, what would be the advantage of Pixi compared with Nix as a package manager? It looks like we have a Nix user.
Yeah, so great question. Nix is, like in terms of what we're trying to reach, it's a similar workflow where you can both do source building and binary building. Nix, on the other hand, is a much more, how do you say this correctly? It has a lot more control, making it much more flexible to set up your whole environment and create this one distribution of what you're wanting to do. So you can actually rebuild also the compiler very easily and go from 0 to the top in one go. It ships its own OS with that. And that is really cool. And we've been really interested in that, and we've really been following how they're building that. The downside of Nix, in my opinion, is that it also brings a lot of complexity. So where Pixi, you have this Pixi TOML, and it feels a little bit like pip in terms of complexity. Nix is a whole different level of complexity, which might suit some companies. It's not available for everyone, and especially for people that want to get started quickly, that want to share their work with integrators that don't have any software development background. We've seen a lot of people finding it too complex to get started with. Yeah, that said, I can only give it a lot of love because the ideas are really cool. It doesn't allow you to ship on Windows, which is the biggest reason for us to not start with it right now. But yeah, it compares a lot, and we're trying to reach the same goals, basically. If that answers it enough. I can already read the next question to continue. Can you create an SBOM for license clearing? Yeah, so let me immediately start with the examples. So if you have a log file, it actually contains the licenses of every package in there. So the log file is basically a non-standardized SBOM we are currently working on making this generatable from these log files, but an SBOM is well defined in terms of format, but it's not very clear what should be contained in these SBOMs. Just like Nix, same person, same question, we can go down. So we can get this package, we can actually see what was precisely used to build that package, and then also go down that road. So what we're currently working on is integrating that we know all the SBOMs of the separate packages, and then create the one overarching SBOM for your environment that then says, I use this package, which has that SBOM, I use this package, which has that SBOM, and then the tooling around that. We're currently still working on that, but in the very basic form, you can already get the licenses from your Pixi log file. Assuming that answers it, I will continue to how are cross-build system dependencies established in Pixi workspaces. Cross-build system dependencies, could you elaborate, Michael?
For sure. You mentioned that in a Pixi workspace, you could as well have ROS packages sitting next to native Rust cargo build packages sitting next to a Python wheel sitting next to whatever. One could reasonably assume that there is some dependency between those packages, that perhaps one of those ROS packages is relying on a library that's built with cargo. How does Pixi take care of establishing the topological order to build things in the right order and making those available so that downstream packages can use upstream packages?
Yeah, great question. I am thinking about having an example for that ready. I don't think I have a cross-language example that is not within the ROS ROS ecosystem right now. But what I can give you is that, for instance, in this example, can you see my screen? I can grow it a little bit. I have a few path dependencies listed here, and some of them are C++ packages, and some of them are Python packages. And because I use the package XML, it will read what's in these package XMLs, and then add those dependencies to the package. This one is like super simple. Maybe there's one more. They all don't use each other, but
in this case, if you were to source build with Pixi, would presumably rely on Colcon, and Colcon would then look up the package XMLs, do topological sorting, and do the build. Now, what happens when you have something that Colcon doesn't recognize, or perhaps is Pixi delegating on the build system? Does Pixi really need Colcon to be able to understand and organize?
No. So what it actually does, it creates these recipes on the go. It doesn't use Colcon at all to read these things. And then it maps these names to a name that it knows. So if you add not just TurtleSim, but the Navigator Pi here, Pixi will figure out, oh, that is Navigator Pi that I need to build first, because you depend on it in the build of this package. And because Pixi is agnostic in what type of package that then is, it can be any package that you then depend on. The mix with the package XML is a little bit harder to define, but what you can always do is in your Pixi TOML, if you add a Pixi TOML to a package, you would add this package, and then you can actually say package.build, for instance, build dependencies, and then define my build deb equals whatever, and that can also be a path dependency again. So that would go to something like that.
Got it. So if it cannot be, if those dependencies cannot be inferred from the package XML or PyProject TOML or whatever, they can be specified at the Pixi TOML level.
Yeah, exactly. Awesome. Yeah, you can always add this, and then Pixi will pick it up. It does the resolution itself. And also for the the package XMLs, it will also do the full resolution itself. It will just first translate it from a package XML to a Pixi TOML internally. You will not see that. Then there's one more question before I do the live demos. Can Pixi replace Docker a way to generate reproducible environments, or does it complement it? So I would say it depends. Classic answer. I really like to use Pixi for basically all development. So if I only care about running the code myself, about setting up the environment to do some building, to do some testing, to do some of that work, I will just use Pixi. I don't need Docker anymore. I can do it cross-platform. I can do it in virtual isolated environments. So it's more than good enough there. Where I still sometimes like to use it is when I then start deploying it to somewhere, for instance, in Kubernetes or on a separate machine where I don't want anyone to care about package management anymore. I just want to ship one image there, and then Docker is a very good tool to use it. Pixi is very helpful in that because in your Docker image, you only do Pixi install, and then you throw away Pixi, and then you activate that environment and you're done. So you can use the log file reproducibility to actually make the building of your Docker image reproducible. And then that image that it creates is obviously, yeah, it's not, I wouldn't call it reproducible. I would call it runnable because you can just run it everywhere from that point on. That's a very good feature. We used Balena when I was still doing robotics, and that made it very easy for our distribution people to host it on a robot for a customer, and we didn't really need to care about it anymore. That was easily handled. That's not to say that you don't need it. I just think it really complements it well in that case. Assuming I answered that, let's go into a little bit more of a demo. So first off, I mentioned that I wanted to show you that it also works on Jetsons, but I'm currently on a Mac, so I had some struggles with sharing my screen. So I will just let you quickly this example, which is on a Jetson that I have at home. I used it to install all the CUDA dependencies. I installed PyTorch with it. I installed OpenCV with it. I installed ROS with it and then ran this command. I can also run this on my Mac. It will not be a Jetson setup then anymore, but this makes it really easy to get started on a Jetson because I know it's really hard to use Jetpack if you've been using that. And that just makes it a one-shot go. I just do Pixi run this command that I pre-built, and then it starts working already. This might not be enough for you, so I wanted to show you what that looks like in the Pixi toml. So if you want to do cross-platform stuff, as I said, you add these platforms here. And for the Jetson specifically, you will add an ARM variant. Jetson has a very specific architecture that you need to build for. These examples are online as well. And then you can say, I need that specific ARM variant built. And because you have this dependency, all the other dependencies like PyTorch and Torch Vision will know which version of themselves need to be installed. Pixi will solve that. Its resolver will pick that up correctly. And then for the Linux Arch setup that you defined, it will start using the Tegra variant. One more thing that's interesting about Pixi that you might want to know is if you want to use CUDA, you need to tell Pixi that CUDA will be available. Because Pixi pre-solves for any type of system, it will pre-solve for the most likely system. And this is where we're still a little bit figuring out how to do this best. But if you have CUDA, you need to currently say your system requirement is CUDA, and then Pixi will assume it in its solve, and then also install the CUDA variants of all these packages on your machine if it has CUDA available. So for instance, on a Mac, I obviously cannot use CUDA, but on the Jetson or on my Linux machine with CUDA, it will pull in the right packages for that. And that allows me to install it anywhere. Then let's go to something I thought was pretty fun. What I built was a setup where I can use ROS on different machines, something that ROS is built for in particular. But in this case, I don't want it to just run it on my MacBook, but I also wanted to run it on my Windows machine and on my Linux machine. I didn't really have a Linux machine laying around, so I'm using a Steam Deck. I know it's not Ubuntu, but again, Pixi, you can just install it on there. So what I did, I installed this exact same project. Doesn't want to see it, but trust me, it has ROS installed on my Steam Deck. It's actually just connected through my network, and I did the exact same thing, same exact project that you're seeing here on my screen. I also installed it on my Windows device. Again, simple ROS, you guys all know how it works. I just did Pixi run one of these tasks. So on my Steam Deck, I run the sim and I run the tally op. on my Windows device, I run the visualization node so that I can visualize it in Arvis. And on both my MacBook, which I will do right here, Pixi run sim, and on my Windows laptop, I can, oh, sorry, wrong one, Pixi run Arvis, which will then start up Arvis. I can control it from my Steam Deck, and I can promise you that it actually controls this sim. Oh, sorry, I am moving into the edge. Let me come back, and then I can obviously demo effect. Why is this not updating now? Okay. I actually don't want to deal with demo effect. There, it updated. It's just a little slow, maybe because I'm sharing my screen. But trust me, on these systems, when I'm not sharing my screen, it was very fluent, and I could just use ROS on all these machines with just that one call of Pixi run sim or Pixi run Arvis. It will install all the Jazzy dependencies that I had. It will install Pygame for me, and with these commands that work on any platform, I can get started within minutes. And that just makes it really easy to use Pixi anywhere. What's also interesting about this, I didn't use Colcon here. I have two different packages, a Python package that has the teleop node that runs on my Steam Deck, and a C++ package that has the visualizer to show the path and the turtle in Arvis. Both have a package XML linked to them with the dependencies that they need to perform the calculations and do the publishing. And then when I run this, Pixi will lock that into my log file. So if I look at teleop, you will see that it has a package XML defined, all the dependencies that are then linked to that package, and then this is locked down. So you guys can now install this package on your machine and trust that it will build because it was built on my machine. We're actually releasing a very cool feature in the new log file that's coming out next week, where it will lock down not just the dependencies of your environment, but also the dependencies of the built environments that have been used. So for instance, in this case, we needed CMake for the Python, for the C++ package, and that will also be all locked down, helping with that reproducibility that we've been talking about. I can show you more, but I know that we're closing in on time. So maybe there's just a little bit more questions that we can discuss, and then that it is it from my side. Thanks for listening in.
Thank you for the great presentation. Let me see if there are any more questions on the list. If not, I happen to have a few.
Shoot.
So you mentioned PixiBag, and you also mentioned, well, briefly mentioned that using Docker to simplify deployment. And I wanted to ask specifically about deployment because the most use cases I've come across with Pixi were more on the developer researcher side, where you're essentially putting together an environment and then just going off that environment to prove a point. But that's one thing, and a reproducible build to deploy to a fleet of robots is a different thing. And it also happens to be one of the so-called reasons behind, or the rationale behind ROS being tied to Ubuntu distributions and curating those and using Debians and whatnot. So what does deployment looks like when you're using Pixi? What are the use cases that your users are starting to develop, or how you come up with some guidelines on how would I go about going from development to production using Pixi?
Yeah, so as mentioned, you can build with Pixi. So what we see most companies do is that their packages, their own packages, they are using in the development workflow as source packages, and then they have a CI setup that then on a tag or on a release that they do internally, they just build a package, push it to that hosted package registry, and then pull it into the environment that they're interested for the customer. So this is very depending on how you're using it, but what we've seen often is that these robotics companies have an environment per customer or an environment per type of customer. So for instance, if you have an HV that runs in a certain type of environment, it will need the same simulation software, it will need the same teleop software, it will need the same UI, and all of that can be pre-built and then hosted on hosting services like Prefix.dev or any other. And then those environments are built into either a Pixi pack or into a Docker image, or if they're still in a very high development throughput stage where they often need to update certain packages, they will use Pixi directly and just pull in these packages and update it on those machines through SSH. And that is currently the best way to ship these items. We also see some people that actually just build ISOs of their whole setup with their specific minimal distribution, and then just a Pixi environment layer on top of that. This is also how you use it in Docker. You're not going to use the ROS Docker or any of these other big Docker images. You're going to use the most minimal Docker that you can create that has glibc, and then install the rest of the Pixi environment on top of that, making it as small as you can. And what can I add to that? Yeah, we're currently working together with other companies to figure out what is actually a deployment strategy with only Pixi looking like if we would not want to use an ISO or a Docker image or these tarballs. We want to do minimal, really minimal over-the-air updates. This is not something I can give too much information on right now, but it's something that we're working on to figure out.
Yeah, that was going to be my next question, how you manage updates. It looks like right now it's rebuild and replace, essentially, that there is no incremental thing yet.
Not if you want to do like A/B setups with like a single command, but what you can always do is if you're on a customer machine and you do Pixi update, it will pull in the latest updates and you can start running again. But yeah, we know that there is an improvement we can do, and especially on the management side of like, okay, I really need to know what is running on this machine. Is it outdated? With all of these CVEs and security vulnerabilities coming in these days, it's very important that you know what you're running where, and we want to make it a lot easier to do the administration around that, for sure.
Got it. And it looks like a question came in. The question is Pixi needed on the target machine? Instead of Pixi unpack, would it be possible to just do tar extract and call the activation script?
Yep. Yeah, so in the end, the Pixi unpack is literally doing a tar unpack and then having the activation script next to it. What you can actually do with Pixi pack is with an extra flag, you can make the tarball itself executable so that you don't have to do anything except executing that file, and then it will do the unpack and install and then run of that activation itself. I am not doing a lot of robotics anymore, so I haven't used that tool as much as I would do back in the day, but and it has changed, so don't call me out on the exact commands, but it's doable and it's being used.
Super, super interesting. And if I may, one last question. During the demo, you mentioned CUDA being, along with libc, at least on that example, TOML, a system requirement, something that has to be available already. Yeah. Is that specific to that demo? Is that like a hard requirement? Are there dependencies that Pixi cannot deal with for some reason? Or could I also bring CUDA with Pixi, or can't?
What you cannot bring is the CUDA, the NVIDIA driver. So the machine has to have a driver installed. And from that point on, you can handle it with Pixi. Pixi ships the CUDA compiler, the CUDA runtimes, the toolkits. It installs PyTorch with the right version. But you need to give it a little bit of information to tell me, basically, trust me, there will be CUDA. So if you solve your log file that preps it for these other machines, you can assume CUDA is available, and that will allow it to solve in a broader space. I can very quickly show you what that looks like on Prefix.dev. So this is our our channel repository. So if you go for the PyTorch, for instance, it has different variants, and these are per CUDA version. And it will have the CUDA version installed here. And Pixi needs to know which CUDA version you're running with so that it can solve for the right version. It's doing this through virtual packages. So it's like, it's a dependency, but it's not something I can pull in. It's something you have to have already. So I depend that you already have CUDA. I depend that you already have this specific version of libc. And then the dependencies will properly be installed.
Right. Okay. Yeah, that makes sense. Is it an assumption, or is it a precondition that is checked?
It's a precondition that is checked. So if you do Pixi info, you will see these virtual packages. And obviously, I don't have CUDA or libc here, but you will see that I have Unix available, I have OS X available, and I have a certain Archspec available. And you can also do like Unix here, or my Linux kernel is whatever, 5.12 or something like that. This is all information you can give Pixi, and then it will, if there is packages that depend on that, which is not a lot, but with AI stuff, you get more optimizations. If you have a newer Linux kernel, for instance, then packages might say, okay, I have a build that works on the oldest machine you can imagine, and I have a build that's very specific to these APIs of my kernel. Then Pixi can figure that out for you, and it will actually pick the right environment if you have multiple of these.
Nice. That's really nice. I don't have any more questions, and we're actually a minute over time. Is there any other question? Does anyone have anything else they would like to ask Ruben? Thank you, Ruben, for the presentation, for being here, and for Pixi.
Yeah, thank you guys. Great questions, and thanks for listening in. And again, if you have any questions, please join our Discord or go to our website for more information. We're very happy to help, and we want to grow this robotics ecosystem together with the community to make it a lot easier to develop this ROS workspaces and probably beyond that. Thank you, guys.